Welcome back to the UGDBF Tutorial Series, and in this episode we'll be looking at the first part of XFLR and XFLR5 and the basics of how to use XFLR5 for engineering your DBF aircraft. So the first thing to really mention with regards to XFLR5 is that the software is currently discontinued. I think it's being, all the new efforts being put into a software called Flow5, which will be paid. For now, XFLR5 is plenty good enough. There's not too many broken things with it, and there's not too much stuff missing. So unless you have large amounts of money to hand, XFLR5 is still going to be a very good starting point for stability analysis and estimation of parameters and performance for UGDBF scale aircraft. Now, one of the key reasons that it's being discontinued is that it is quite a finicky piece of software and it is quite unstable and things change a lot. Now there's two things you need to really look out for with file formats. They will either be a .wpa or a .xfl. Now if you have a .xfl, you're going to need XFLR5 version 6.10 or above, and if you have WPA, you're going to need XFLR5 from earlier. With regards to the actual software itself, the only real GUI changes happen, I think, in 6.30 something. I'm still on 6.10 because 6.30 odd currently does not render 3D graphics on my system. I don't know why. It's just a quirk of XFLR5, and that's the most important part. The key takeaway is if you're getting into XFLR5, be prepared to maybe download 2 or 3 different versions and switch between them depending on what you find your workflow needs are and what the people around you are using. Second point is with regards to aerofoils, we're going to have a look at importing .dat files and how we can use splines to our advantage, as well as some of the tools available with XFLR5 to refine some aerofoils. We'll go over some sensible Reynolds numbers for analysis, what you might want to run, what the spacing you might want to run might look like. We're also going to define a basic wing, and we're going to run a basic lift analysis of a wing. So the workflow for this is actually quite straightforward. If you want to have a look at obtaining DAT files, and if you have any issues with regards to the ordering of those points, that's covered in episode 2 of this guide. Go have a look at that and come back. Obviously, you don't need to look at the whole thing. It's just all the stuff that's done with calc and spreadsheets to fix the airfoil data up and to sanitize it for import. Then you may find you need to tweak the airfoil smoothness. So the way that it works with DAT files is you have individual panels, and if the discontinuity or if 2 panels form too steep of an angle, the methods, which is for XFLR5 XFOIL at its root, can lead to some interesting behavior. So there's a few tools available in XFLR5 to sort that sort of stuff out, which I will go over at the import stage. Then you would normally do a batch analysis where you would have a look at how your airfoils perform for a huge range of Reynolds numbers, and it would basically, for every angle of attack, plot the performance characteristics of your airfoil. XFLR5 at its core functions like a very large, very complicated interpolator where you will analyze specific points of performance for an airfoil, and then when it goes later to look at, when you want to look at very specific use case scenarios along the span progression of your wing or different chord angles, that sort of thing, it will generally interpolate all those points. So the better your data at this stage, the more accurate the data is going to be at the end stage. You can speed things up tremendously at this step, but being more strategic with how you do your analysis at the entry stage in the batch analysis is going to largely impact not only the accuracy of your results, but the range of results that you can get. For example, if you were to only set a -5 to 5 degrees angle of attack analysis window on your airfoils, during the stability analysis, if at any point a particular case were to go outside of 5 degrees, then it would not be able to interpolate that, and that would give you no data at all. So this is really a crucial step to get the data that you need to actually do useful things with XFLR5. And then to finish up, we'll define a basic wing, which is very quick, and go into the basics of wing performance with XFLR5, which again is quite quick. The most of the time will be on batch analysis. So let's jump right in. Upon opening XFLR5, you'll normally be greeted with a blank screen, and XFLR5 is actually directed into 4 main modes: direct foil design, inverse design, direct analysis, and wing and plane design. And normally if you're starting a new project, you're going to want direct foil design, which will present you with the sort of default spline. Now, XFLR5 can generate knock of airfoils. If you, for example, want to generate a 4412, you come in 4412. I'm not going to work 4412. Set in the number of panels you'd want. So what is important to note is some of the data entry screens in XFLR5 are terrible, but if you don't have enough panels, if the discontinuity between individual panels is too high and you have an edge, you can end up with some very interesting behavior just in the way that XFoil works. So actually, let's demonstrate that. If we do have one with let's say 50 panels, okay, on a 4412. What we'll find is near the front we have some relatively interesting behavior where we have these discontinuities. Now, one thing we can do typically is to refine the airfoil globally. This normally would solve most of your issues where you would have like just single discontinuities. It effectively works like an interpolator, and it just smooths out your airfoils. The other thing to do is to make sure that your airfoil is derotated and that it is in fact normalized. What that means is that the center line of the airfoil, the tip and the leading edge and the trailing edge both line up to 0 and 1. Obviously, if you have a rotated airfoil, so if you were to set up, if you want to, one trick would be to, if I did this, for example, this effectively is an airfoil that is at an angle of attack of a few degrees already, so this tip will need to be up here. Otherwise, you'll find that increasing camber like this exponentially increases lift, but not really. When you think about it, really what you're doing here is increasing the angle of attack of the airfoil, not necessarily actually making the airfoil more performant. So, assuming you're brave and you want to design a new airfoil, what you can do is also you can store a spline as an airfoil. So this is what we call this junk. We can then install this as an airfoil. So. The other thing to make sure, which I think is mentioned in part 2, is that not only should your airfoil start and finish at the 0 and the 1 point, but it should really be closed at the trailing edge. There's not really an easy way to do this. Besides, the only thing I would generally do is to export this to a .dat file, and then go ahead and gedit that DAT file, which I think I'll say that's NACA 412. There we go. And then come in and basically fix this last coordinate point to a 0. And then go ahead and re-import that airfoil. So, foil, where are you? Oh yes, this is old. Okay, so we just basically just do open, we find our .dat, and typically that is enough to work. And yeah, so now this last panel has closed up. That's the main stuff to really watch out for when you bring in airfoils. We're going to remove this junk foil. I don't particularly like that very much. Yeah, so we're going to look at this 4412 because that is the meme. All airfoils at UGDBF are required to, in some parts, or it's for some way, shape, or form, be a 4412, and we just modify the same airfoil. So when you're doing an analysis, you typically are going to want to do a multi-threaded batch analysis, and generally what I'd recommend is starting out at 1000 Reynolds, going up to 10,000 Reynolds in increments of 1. We can update the polar view. I generally run -15 to 30 increments of either 0.5 or 1, depending on what kind of rush I'm in. Let me just double check this is all fine. It's fine. Newer versions of XFLR5 will actually tell you how many cores they want to run. I think this version just uses all of them. So, okay, in this case, everything's analyzing quite nicely. Now, the one thing to watch for is... Okay, well, let's get this running a bit more points real quick. So I'll do 10 to 100,000 in 10,000s. Analyze those. If you see these straight lines between 2 points, generally what that means is, so like this here, see if this carries on. Right. Oh, none of this is giving me flat straight lines, but okay, so you get points like this, but if you get a straight line like this, sometimes means that there's a point here and there's a point down here and it's interpolated everything in between. Large gaps like that can mean you need to go back and to the airfoil page, to direct foil design, and refine the airfoil globally, locally, or in some cases, if you have some really broken geometry, get the splines, spline over the airfoil shape that you have from the DAT file, re-export that, and then try again. It just works the way that if you read into how XFoil the 2D methods within that work, some shapes just lead to incorrect behavior. In this case, everything is progressing relatively linearly or smoothly, and we don't have large discontinuities all over the place, so this is borderline acceptable. These jaggies are not great, but again, they're not the worst I've seen. And so this will be 10 to 100,000 in 10,000s. I'll then normally do 100,000 to a million in 50,000, and then I'll do a million to about 5 million in 500,000s. Generally, it depends what Reynolds number you run at. I think we spend most of our time between 10,000 and a few 100,000, so that's really the range where you want to make sure that you have quite good resolution in quite a lot of points. So which one is at 50,000? Hopefully this doesn't take too long. And through the magic of editing, that's all been run. Now I've just finished running 1 million to 5 million. Now there is one thing to note, which is obviously DBF scale aircraft. Why would I ever need a Reynolds of 5 million? And the answer to that is very simple. With the variations in chord on both of your main lifting surface, be that your wing, biplane wing, or your full flying wing body, from the tip to the root, as well as at different angles of attacks and different speeds. When you do the stability analysis, you may find that in some edge cases you are in the many millions of Reynolds, so this is why you need to run these points. But in general, this is what you'll get. In this case, we have nice CLCD progression. This is fine, so I'm not too worried that anything here has gone terribly wrong. No discontinuities on this one. No discontinuities. Okay, and the final step of actually defining a wing is to go to the wing and plane design. I'm just going to dump this over on the side, and we will go ahead and define a new wing. Can I make a wing? Does this version not allow me to define a wing? I guess I'd have to define a plane as is. Okay, so defining a main wing is actually quite straightforward. It's the same system throughout XFLR5. What you'll generally define is actually only on the one half. It assumes a symmetric wing. So let's say in this case we've got a 1 meter span on each side. So this is a 2 meter span, as is demonstrated there. It's a tapered wing. We can actually change that to be a so we can either taper the front or the leading edge. Basically, this offset controls how far back in X. So if I were to set this to be 0.5, we would have a crazy sweep. Sorry, that's the root. We need to change that to 0.5. So we could have a crazy sweep, and that's how we'd control not necessarily just the sweep, but if we were to set that to 0.18, 0.11, 0.07, we can have a straight trailing edge or a straight leading edge. We can also set a dihedral angle if we were, for example, this is more useful for tails. If you need to look at a Y-tail aircraft, we can set dihedral. And we can also set a twist. If I remember positive, yeah, positive is extra angle of attack. So this is effectively 15 degrees extra angle of attack at the root. And you can insert additional sections if you need. So maybe you need you want to do most of the tapering in the root. You could do that sort of geometry. You can change the airfoils, and what this will do is will let you blend between airfoils between one section and the other. And that's the bulk of defining a wing within XFLR. There is one other thing to consider, which is the panel distribution. So if we were to run the outline, you can see here the vortex lattice method panels that XFLR is going to use, and this is actually controlled. I need to get my axes in here. This is controlled by these parameters over here in the last 4 columns. Now, there is one thing to note. The X direction panels, you probably don't need that many. I typically would go for something that, when you zoom into it, doesn't look completely terrible. And this will look pretty terrible if I zoom in on that leading edge. We can see here you've got this triangle section. This is not great. Now, the way that you can fix this is, well, the way you make it worse, typically anyway, is by going to uniform. Uniform's bad, so you can use cosine distributions where it will concentrate the majority of the panels at the leading and trailing edge, which is exactly what it's done there. Typically, you don't have much curvature on the middle edge of the wing, so you don't need a huge number of them there. You can also do the same thing in the Y direction, and this is where things get far more interesting, because you can look at, for example, the full wing dynamics, or if you have specific interactions around inflection points on discrete sections of your wing, where to mix, or your these inboard sections and outboard sections, you can also define them that way. So in this case, I am normally a fan of cosine for sections like this, or maybe even which one's the one which concentrates at the tip? Minus sine. Yep, this I find quite palatable. I'm normally a fan of cosine. Uniform isn't terribly bad as well if you have computational time for it. The thing I will point out is that the stability calculations, when you come to do those, will actually, the matrix size that you're solving is directly proportional to the number of elements that you have, so you do need to be quite careful how you size the number of elements that you use. This is, for now, is fine. We'll go ahead, save and close this, and we'll define that as our wing. We'll just remove everything else that we don't need. And the other thing we need to also define is the inertia. This will be very important for stability calculations, but we can define, for example, the wing mass as 1 kilo. Okay, we now have a wing. It is defined. It has mass, and we can start running a wing analysis. So in this case, it's just a dumb analysis for the wing. We can either fix certain parameters, so in this case, just a fixed speed at 10 meters per second. That's 36 k's an hour. Is it? Yes. That's sensible. I think our takeoff speed is actually close to 14. Quite fast, but when good wing loading is always a plus. You have different analysis methods. LLT, obviously, if you're in, I think, 3rd or 4th year, you'll have covered at least LLT, maybe one of the maybe VLM2. But LLT generally is fine. Lifting line theory is generally good enough for a plane up wing. For a straight up wing, we use the plane's inertia as defined. You can override this if you need, and we are going to set everything else. So okay, hooray! This is always one to check. In older versions of XFLR, it would always round to 0. I'd always put in 1.5 v minus 5 just to make sure that it's there. Other than that, everything looks good. So we can run that. So actually, once we've defined the analysis, nothing actually happens. This is not like the aerofoils. We need to actually define, for example, a sequence of angles of attack. We'll start between minus 5 and 15. And then we can actually run the analysis. This generally takes not very long. You'll see here there are a number of angles of attack where it is unconverged. The reason it is unconverged is either we haven't reached the conversion criteria within the 100 iterations. We can easily expand this by going into advanced settings and saying, hey, we want, for example, 500 iterations. With a number of panels here, this is actually quite fast on a modern machine. And it'll actually tell you here that it hasn't converged because at certain points, for certain angles of attacks, for example, I think where we put the 15 degrees, is that quite close in? Yep, span past 0. So where we put in the extra 15 degrees of angle of attack in here when we defined our wing, and we're adding an additional 12-ish degrees plus the relative wind direction, U infinity, I think, as Dr. Green put it. We're actually above the maximum point that we simulated for what we analysed for that Reynolds value on the on the batch analysis we did earlier. So this is actually where you'd be limiting yourself if you did a very small number of angles of attack. Anyway, we have most of our data, and if we go change over to plot view with this button, we can actually see how our wing performs CLCD, coefficient of lift versus coefficient of drag, lift with alpha, and we can actually change these graphs. I'm not a huge fan of the CLCD polar. This is, I find, not very useful. I much prefer, if I could get this graph, where are you? Current graph, define graph settings. I am much more a fan of lift versus alpha, especially if you're looking at we would probably need FZ in that case. There we go. So we can actually look at how our lift force changes with our speed. Keep in mind, in this case, we have a fixed velocity. So in some cases, you may want to switch the velocity for the force. But other than that, that's the... Oh, that's a crash, but that's the main part of XFLR and analysing a wing.